Now, the title is calling Looking for Geons, so I will not be claiming that we saw them, but what we did and what could be optimistically interpreted as hint towards that. Okay, so first of all, what is a geon? Well, the idea is actually fairly old, about 70 years, and has already been phrased for general relativity in a classical theory. And basically, the idea is not so different from a soliton. So it's a propagating particle-like gravitational wave, so bunch of gravity. However, in the classical theory, it turns out to be unstable, so they would decay very quickly again. Now, in a quantum theory, where you think about gravitons as the quantized excitations, such an object would be something like a self-bound graviton. So not so dissimilar from the idea of a clue ball in QCD, basically a lump of quantum gravity. And already 30 years ago, it has been mused by people that this may be more stable than the classic analogous and may exist in quantum gravity. And if you just go a bit further, of course, if you have a pure gravity theory, you have Schwarzschild black holes in the classical solution, and if they exist as a quantum level, the only thing out of which you can make a Schwarzschild black holes is from gravitons. So in a sense, these geons could be to black holes what nucleons are to neutron stars, namely the constituents of these objects. Or if individuals of them are stable, then this may actually be also dark matter candidates and may form like primordial black holes in the early universe. So the question whether geons exist or not is a very interesting one, and I will report here about our investigations of that. But if we want to look for geons, it's not so trivial to actually answer the questions, do they exist? So if geons should play the roles which I just lined out, we need a propagating massive particle-like states, which exist even in pure gravity. But as you all know, gravity is different from ordinary theories. So what does particle-like anyhow mean? What does propagating mean? What are admissible states in such a theory? And so these questions need to be answered alongside. And probably the answers to these questions, also whether geons exist, will probably depend on the theory. And here, I basically will use a path integral version of Einstein-Hilbert and assume that the theory exists. And since I will be using causal dynamical triangulations later, I assume that it is what I described in terms of causal dynamical triangulation, for which there is some significant evidence, in my opinion, that it is true, but of course there's an assumption inland here. On the other hand, I can take a cue from experiment, because the questions up there also apply to gravity plus matter. What does particle-like mean in a gravitational theory with matter? But obviously, particle is a pretty good concept in our everyday life. Everyday means things like CERN or so. So it appears that there are many orders of magnitude where the idea of a propagating massive particle makes at least approximately sense. So it's not so far-fetched, the idea that this could actually exist. So what will I do? First of all, I have to choose suitable objects to study. I have to think about particle concept, and what turns to my advantage here is that you can find something which is very similar to the Brout-Englert-Higgs effect in quantum gravity. I will show you support for that statement. And then I can use the Fröhlich-Markov-Strozzi mechanism to define what a possible candidate for a particle could be. And after having formulated that, that motivated how we looked at the causal dynamical triangulation simulations, where we did the simulations, and I show you some, I would say, hints that such a geon could actually exist in pure gravity. And after that, these have interesting consequences also for spin and supergravity, where if I have still more time, I'll say a few words on that, because that is, of course, connected to that. Okay, so that's my setup. As I said, it's a quantum field theory setting. There's no strings or other non-quantum field theory structures. So basically, I have this kind of path integral. Now, which means I have standard gravity as Einstein-Hilbert, and I treat diffeomorphisms basically like a gauge symmetry, which you can do also already classically. So I can transform using diffeomorphism my coordinates, and just like a gauge transformation, it shouldn't affect observables. I have to integrate, of course, in a perpendicular with variables. And basically, you could expect that any choice will give you a different quantum theory. And lacking experiment, we have no idea what the correct choices are. On the other hand, in such a setup, we know that when we factor out diffeomorphisms, we basically have to look at manifold topologies here. Still, there are, just like whether you integrate in quantum electrodynamics over the electric field or the gauge field, you get different theories. And so we will see what I will use in the following, but that's by no means unique, though I think much of what I've been saying is relatively independent of the choice here. And then, if you like, we can add other fields to the game, but I will not be talking about matter-coupled theories here. Basically, the setup is the same as you know from the FRG asymptotic safety approach. CDT, EDT are all very similar and the basic ideas behind that. So I'm not having here something very exotic for you. Okay, now, of course, if I have a perpendicular, I need to calculate an observable. And of course, I would like to have that the observable is non-zero. There are two possibilities how I can do this. If I don't want to look at a gauge fixed scenario, diffeomorphism fixed scenario, then the only choice I have is that this is an invariant quantity. Otherwise, this will average to zero. So that means I have to be locally symmetric under diffeomorphisms, locally invariant under Lorentz transformations. And if I have matter, then I have to be locally invariant under gauge global transformations. So I need a genuine invariant quantity to even make statements. But in the end, when I want to talk about Geons, I need a correlation function which characterizes it. And that is what I need to do. In particular, the metric is completely useless for this purpose because necessarily the average metric needs to vanish. The reason for that is simple. If I just integrate over a manifold structure, there is no preferred events. And anything which depends on events in a single event, like a metric, can therefore not be non-trivially existing as long as you don't fix coordinate systems. You need really something which is maximally symmetric. So any observables need to be diffeomorphism invariant. Metric isn't, so it's not a good observable for the following. So space-time cannot be characterized by a metric. The only thing which I can use are space-time invariants, like curvature scalars. Local observables, because there are no preferred events, can only be non-trivial if they depend at least on two events. So at least a composite object is necessary for physical observations. Again, you can build your objects then from local curvature invariants. That is what we'll be doing. And finally, distances is something which I need to rephrase also in a diffeomorphism invariant way, because otherwise I again have the problem that they're not independent, so I cannot formulate them using coordinates. Best choice here is probably geodesic distances, and that is also what I will be using later on. That also means if I want to talk about the space-time structure, the average metric is probably not a good idea. So we need characterization of space-time by invariants. Simple objects would be things like that. You integrate over the curvature scalar and normalize by the volume form. This object can, of course, only be a constant because there is no preferred event. So we have a number of independent invariants, and that is what we can use to describe it. So the space-time needs to be on average, the quantum average, homogeneous and isotropic. So if you want to have a relevant space-time, the only options which you can have in such a theory is that it becomes flat or anti-de Sitter or de Sitter if you have Einstein-Hilbert gravity. Of course, you can have things which are different, but they will not be extended space-time. We know of examples of that in CDT. And the invariants then identify my particular type. The simplest non-local, the simplest object which is not a single event, and therefore not be constant, needs to be something which is composite, and the simplest object you think of is a scalar particle, described by a scalar field that is by construction invariant. So the simplest object which you can think of is a propagator like that. As I said, always some scalar field. The argument is, of course, an event. It is an identification which is not given by coordinates. So you need a characterization of x and y not in terms of coordinates, but underlying event structure, so the mapping of the manifold structure the underlying are for. The result will depend on the events, but events is not really a useful argument because we don't know how we should track events across different field configurations in a path integral. Also, events cannot be invariants. So what we really need is some kind of distance function R, which again becomes a quantum object because the distance between two events on different field configurations is in general different. So you need an invariant formulation, and one which has been advocated in the literature and which we'll also use here is that the difference will be characterized by a diff invariant distance, and therefore the simplest choice here is a geodesic distance between the two events. And here I particularly use a minimization in case that we have this. That also means that distances here can only be along paths which are entirely time-like, space-like, or light-like in the following. And of course, if you have a space-time which doesn't admit geodesic constructions, you need to do something. Fortunately, the CDT formulation will be allowing to do this. Okay. So in principle, calculating the distance between two events is a separate calculation, and indeed, that's what we need to do. That also means that propagators will not be depending on anything else but the distance. And again, this is only a true statement here if you don't have special events in your system. So if all events are equal from the point of view of physics. In fact, we already do exactly that when we talk about flat space quantum field theory. There's nothing generally new. The only advantage is in flat space quantum field theory, all of that construction is entirely trivial. And in particular, every field configuration has the same result here, and therefore the expectation value coincides with the trivial calculation. Okay, now we want to discuss this in more detail. So now we will use causal dynamical triangulation. I will go not to the technical details, just give you a flavor of that. But first thing is only use pure gravity, so matter goes out. And in CDT, I replaced the integration variable with the topology of the manifold, basically with the collection of distance measures between events, which is a diffeomorphism invariant path integration measure. And I also make the choice so far to causal structures. So I restrict my possible manifolds over which I integrate here to Fourier-able pseudo-Riemannian manifolds with fixed global structure. So in particular, a fixed spatial structure. That is the setup of CDT. And then you discretize this using Regge calculus. Basically, you are discretizing your manifold in terms of simplices, which is, basically tetrads with some of its edges time-like. Technical details I don't go into. There are excellent reviews on that, and would be bore you here. And then I perform a Wick rotation that is well defined in this restricted setting, mainly because of variability. And that means I have now here a minus sign, and that allows me to do the whole thing using standard Monte Carlo techniques. So it's like lattice quantum field theory, just more complicated. Of course, because I'm doing a Monte Carlo integration of that thing, I will have statistical errors, and I will have systematic errors because I discretize. And that means I have usually a finite number of systems, finite number of simplices, and a finite number of time slices, foliations. And this also means I have a systematic dependency on the extension of my simplex edges. Still, same ideas as you have in standard lattice field theory in flat space-time, and you have to track these things, of course. Here I will exclusively choose a global structure which is periodic in the foliation and temporal direction and spatially spherical, and therefore I can identify my discretization in terms of the number of time slices, basically, and the number of simplices. Okay, and that is how it looks. That is an observable. What do I have here? Now, I plot the cube root of the number of simplices as a function of what I introduce as so-called cosmological time. This basically works by I take my volume and I have these time slices and I look for each time slice what is the largest number of this and set this to be cosmological time 0, and then I have this direction. Of course, the maximum volume is constrained by a causal finite system. And of course, you could replace this number by the maximal geodesic distance. It turns out that both observables don't disagree in any meaningful way, and that is, of course, much cheaper. So this is really a good approximation of the structure of the CDT spacetimes. Again, there's nothing new about this. This has been known since a long time that you get this. But for me here, it's important that this identifies what I will call cosmological time in the following. That will be an important concept. The thing is periodic because I choose periodic boundary conditions in time. Note this is also here in a logarithmic scale. The spatial profile has been seen by many people over the time to be consistent with what you expect from an Euclidean de Sitter space. So you can really think of this as a proxy for the radius. There's an interesting thing, because de Sitter you have a phase where you have a rapid expansion. Of course, it is Euclidean de Sitter, so it's not really an exponential behavior, but it's exactly what you expect for the structure. Now, the first interesting observation is if you don't plot here the average value, but you plot here a histogram of the individual configurations. And what you see is here that the profile and the histogram of the individual configurations look very, very similar to the average behavior. So you have an average behavior and you have very small fluctuations around it. Again, that is not something new. Just plotted here, perhaps in a different way than usual, but it shows you that we have a very small quantum fluctuation spacetime for this set of parameters. Now, the important thing is that if I would now introduce a gauged fixed metric by fixing a coordinate system, that means that the metric could be fixed to be something which is extremely close to the de Sitter metric. That is also something very interesting because also in general relativity, in classical theory, we know that we can basically describe very well the dynamics of space-time, which we observe by a metric which is very close to exact maximally symmetric solution. Now, there's not a big jump here to state that we do observe here the same effect as we would have a Brout-Englert-Higgs effect in split space quantum field theory. We see basically a classical solution with very small quantum fluctuations around it in our metric field. And of course, then also in this derived observable. And that is, I think, a very important insight that the Brout-Englert-Higgs effect works also for quantum gravity, at least in this formulation. And we'll be using that in the following. We can also consider this from other observables. One of the things is, of course, you would like to calculate the curvature. Now, the curvature is not directly observable in this concept, but what has been introduced almost 10 years ago is the quantum curvature, which basically is the area of a surface with the same distance to a point, so what would be a sphere, a spatial sphere in flat spacetime. And so you can determine the curvature by comparing this basically to what you would have in flat space. And now you see also here that the average value is fairly shapeless. It is a bit strongly curved here. And indeed, you can interpret the result in terms of curvature because basically as a function of this distance, this will be determined in the continuum limit by the curvature scalar. So indeed, this is a measure for the curvature of the system. So it's really a physical information which we see here. And for the most purposes, I have a fixed delta to a specific value, but we will see later on that the main results of what I'll be talking about is independent of that because we can access also R. Also interesting is that the fluctuations around this are very, very small. So you see we have fluctuations extremely small of this curvature, which exactly is, of course, what you expect from a Brout-Englert-Higgs effect. So we see that also in the curvature measurement, this behavior is reflected. Interestingly, this particular value here peaks around also this rapid expansion. And this is a behavior which we will see again and again, that this is a very characteristic scale for the whole system. Note that this is only because of cosmological constant. It's still Einstein-Hilbert, we don't have inflation or whatever. And it's also the Euclidean version of this rapid expansion. Okay. Now that means I automatically get the zeta, but shouldn't I care about the fact that that is not the spacetime we're looking at in reality, because we have a Big Bang. Now, a Big Bang is a preferred event. So something like that is not allowed in a path integral formulation. You cannot have that. So, of course, the natural question is, what is the description of a universe in such a context? And the answer is the only thing how you can describe asymmetry is in terms of correlation functions. So if you want to ask, what is the probability that everything was concentrated at one point in the at one point in your evolution, so at a single event, and then afterwards it is expanding, that is the thing which you would calculate. You look at something which concentrates everything on a single event, and then you go in future time-like direction and look at objects which are at space-like separation. But that is basically the situation which you would have in a decay process or in a type of scattering process. And that is then something which tells you, for example, by looking at this as a probability, what is the probability to get certain extents of a universe and time. So that is the way how in such a path integral formulation you would have to look at something which is a Big Bang behavior and see what comes out. That, of course, is far too complicated at the moment. So I will, aside from this, not say anymore, but that explains why I have always this zeta structure for the moment. Okay, now I have my space-time where I want to look for Geons. As I said, Geons should be particles. And how do I identify now particles in just a de Sitter-like system? This is a thing which has been discussed at length in the literature. And I opt here for not finding the perfect answer, but really the only thing which I want is something which approximates the concept of a particle for our purpose of, say, our solar system or our galaxy. I need only something which makes particle-like behavior approximately true over some intermediate distance. That's sufficient. Empirically, I don't need more. Now, but how could I characterize that? Well, in flat space quantum field theory, particles are only defined via the LSZ construction. And the most important statement from the LSZ construction is that it doesn't matter which operator you use to create your state, just the quantum numbers. And to really define particles, what you need to do is you have to look at operators at asymptotic space-like distance and use cluster decomposition. Now, the second part here, that is probably not true in quantum gravity, especially because what is asymptotic space-like distances in a universe which has a malleable structure? That means what I'm looking for as an effective theory is taking a cue again from astronomy and experiments. Particles are a good concept at intermediate distances, and that means we're looking for effective particles only. We're looking in a distance window where we have almost operator independency and almost flat space behavior. And if I see this, then I start talking about a particle, because that's also how a particle will behave in our universe. So I need to look at different operators creating the same state, and I have to look where I see flat space behavior. Okay, now where can I see this? The Brout-Englert-Higgs effect will give me a cue how to look for that. And for that, I use the Fröhlich-Markius-Strocki mechanism. So again, the question how to define the Geon as a particle. Because the quantum fluctuations around the classical solutions are small, I should use this information. But still, diffeomorphism makes it a gauge theory, so I need to look at composite diffeomorphism invariant observables. That's exactly the area where the Fröhlich-Markius-Strocki mechanism works, because you expand the expectation values in quantum fluctuations. It's not a background field approach. You do this really on the quantum field level. You don't have a background field. You never introduce it. And then you use the fact that more fluctuation fields will usually create suppressions. Assumption seems to be working, and it works exceedingly well in flat space quantum field theory, where we understood this mechanism. Now, how do I apply this to gravity? Well, as I said, the CDT universe seems to be well approximated by a classical metric. That's due to the parameter values, so it's very, very special. It's not something which is generally true. But it fits with our empirical results about our universe. Quantum fluctuations of metrics are also not particularly large in our system at large scales. So what we do is an FMS split after I use a convenient gauge fixing by replacing after gauge fixing, not as in background field methods before, the metric by a sum for classical metric and fluctuation metric. You can also do product or whatever you want. This is at leading order. This will be irrelevant with how you split it. And you assume that this quantum part here is classical metric, of course, needs to be useful. You should not have special events on the Friedman metric, but something like the de Sitter. And you need to have a suitable gauge checks because the split happens after gauge fixing. The annoying thing about quantum gravity in comparison to flat space, where you can do the same thing, is that you cannot write down a linear condition. But a suitable choice in our investigations has been Hayward gauge, because it turns out to have relatively simple solutions. Unfortunately, because of the nonlinearity, inverse fluctuation fields will not be simply related, but you always have a Dyson equation for that. So you have an infinite series at tree level. But because you assume that higher orders are suppressed, that usually will not be a serious problem. Okay, how does this work? Now, remember we have this distance function here. And now I apply this to the distance between two events. Then I have the classical part and I have this fluctuating part. But the classical part is just the classical geodesic distance, and then you have a small fluctuation part from the quantum effects. So the leading order in this approach, using the Brout-Englert-Higgs effect, using this mechanism, we see that the universe exhibits quasi-classical behavior, very much in line with what we observe. In particular, we get at leading order a totally classical space-time, and the quantum fluctuations are corrections on top of that. They will be, of course, then hard to calculate, but they are there. For propagators, similar situation arises. You expand this, and now have a double expansion in the argument, which I write here as a Taylor series, plus an expansion for the correlator itself, where you have to take the expectation value in the quantum fluctuating field. The leading term is automatically the flat space propagator. Now that means we indeed see that the full quantum gravity propagator becomes, in a leading part, systematically the classical particle. So it really becomes like a classical in the sense that it is a flat spacetime, or whatever spacetime you choose, propagator. And therefore, there is a systematic way in which flat space behavior arises, and you have systematic corrections to that. As I said, you have the distance effect, and then you have effects for metric fluctuations. So this shows you how particle-like behavior systematically arises in quantum gravity, because if you have this Brout-Englert-Higgs effect as a leading term, always flat space quantum field theory, and then you have corrections which are systematically obtainable. This has, for the scalar part, also been consistent with EDT results, which show this behavior. And moreover, we have a controlled limit of setting the quantum gravity fluctuation field to 0 and automatically, smoothly merge into flat space quantum field theory. That's also nice, because that means in our setup here, Swampland becomes a parametric effect. If I have a Brout-Englert-Higgs physics, I end up with flat space quantum field theory. If I don't, then in general, I will not end up with the theory being flat space quantum field theory. So the Brout-Englert-Higgs effect here really controls the low energy limit of quantum gravity. That's very convenient. Okay, so that means basically, since we have the Brout-Englert-Higgs effect, we expect that correlators will indeed show on suitable distance scales particle-like behavior. Now, let's look for that. As I said, it's a pure gravity excitation. And since the only diffeomorphism invariant operators I have are curvature scalars, the Geon needs to be described by a curvature correlator. So something like that. Curvature scalar is the simplest object. If I apply the same thing to it, it turns out that to leading order, this correlator will have a differential operator in front, and then you have the ordinary graviton propagator here in the ordinary space-time distances. If you have flat space-time, it turns out that this thing vanishes and you don't have propagating modes at lowest order. The reason is the structure of the differential operator. Trying to do the same thing for the zeta is actually not so simple. We don't have the answer yet. But the important thing is you really have this projective behavior that the curvature scalar is given in terms of the graviton propagator. And that is now what we test in CDT. Okay. So as I said, we look at a diff invariant composite scalar operator. We are not the first who've been looking at that. In the continuum, we would need this object. And of course, we have to normalize it such that trivial volume effects are divided out, so divided by the correlator of unit operators over space-time. And in CDT, I start by looking at the fluctuation operators of my quantum metric for that. So these are the objects which are most directly to calculate. And so I'm looking here basically at the connected part suitably normalized to trivial volume effects scattering out. And that is what I get. So here's the correlator. Now, first of all, we did this in spatial direction, mainly for various technical reasons. There will certainly be more about this in the future. So that is a spatial distance, and I do the calculation right here on the largest time slice. I will come back to the others later. And here I have the unrenormalized propagator. And just give here's the average value, the number of simplices. So, of course, we have fluctuations in that. And these are the direct data. And you see we have fairly large errors around that. And this is the behavior which we see. So as I said, it's a resultant maximum spatial extent. For spatial correlation functions, we expect exponential decays. That is what we get in flat spacetime. And indeed, this is what we see. At short distances between, in this range, we see an exponential decay of the correlation functions. Maybe at very short distances, some discretization artifacts, but then we have a nice, more or less smooth single exponential decay. So in particular, we can associate mass with that. So the behavior in this region here is really the one which you expect from a massive particle in flat space-time. It doesn't keep that way. So first of all, based on the arguments which I've given you before, that may, if you're very optimistic, interpreted to be a signal of a self-bound gravitons described by the operator based on the argumentation before. So basically a gravity ball similar to a glue ball. As argued, this doesn't hold. And after the exponential decay, you get non-exponential behavior at very long distances. Don't forget, we have spherical boundary conditions, so we start to see here overlap effects and a behavior which turns out to be less than linear. It cannot be described by an exponential. So we have a behavior in the first distance window close to the average size, which is exponential, and then afterwards in the regions where we start to see fluctuations of the universe size, things like that, we go into a linear behavior. This is only from a single discretization, and there's a hell of a lot of systematic errors which need to be discussed. So I take this to be an interesting hint, not I would claim that we observe the Geon here. The volume is also decisive, so I plot here the results from two different volumes. The blue volume is giving me the behavior from a larger volume in terms of simplices and also in space, and the other one gives you the behavior at smaller volume. You see similar behavior. It actually turns out that the masses are very compatible. Both are exponential decay, and the main difference is the morphing into the linear region, which is described by changed by the volume. But the mass associated with this exponential decay turns out to be, within statistical errors, to be fairly independent of that. So it's really long distance behavior which fields the final volume. We also managed, at least for the simplest case, to extract the continuum curvature scalar by doing the calculation at various values of this delta parameter. It's statistically annoying. And here is the result for the correlator. We see the same qualitative behavior. And in fact, the fit here uses the same mass as for the original Q operator. So we see that even in this continuum version of the curvature scalar, we see a behavior which is consistent with an exponential decay. This was only possible on the smallest volume, so we see this moving to a closer value here, also in this one. But that means that even in this object beyond the trivial, this proxy quantum curvature scalar, we see indeed the exponential decay in the physical curvature scalar operator. So that's very interesting. Okay, now here I plot for you the mass as a function of the cosmological time. So this is calculating the correlator at every cosmological time in spatial direction, extracting the mass of this exponential decay and plot this as a function of that. And people have independently of us, long before us, determined the spacing in terms of the Planck mass. So I can give you the result for this mass in terms of the Planck mass. And what we see is that this is of order of 0.1 Planck mass, the characteristic mass. At the same time, the spatial volumes here are some 30, 40 times the Planck scale. And we see that we have a distinct behavior. There are statistical errors, of course, which are very large as a function of the cosmological time. From the largest extent to the smallest extent, we see at the point where we have the fastest change that the mass grows almost an order of magnitude. Indeed, if I overlay here the results which I showed you before about the statistical features of this universe, here is again the mass. That's the size of the simplices. Roughly here is somewhere the inflection point. So we see that as we enter the inflection point, we see that the mass is growing. And we see this also happens fairly before, after this peaking, roughly at the peak of the fluctuation field in the so-called calculated delta Q for this value of Q. Again, that is roughly at the inflection point of the quantum curvature scalar. So we see that here the space-time structure imprints itself on the mass. And that, I think, is an interesting thing, because if this should be true, having a mass which depends on cosmological properties would be, of course, an interesting phenomenological option. We also find that the whole thing is fairly independent of the volume. So here we have 3 different volumes and calculated the mass correspondingly. We have normalized this to the point of the maximum. We see that on the largest volumes, we have less beyond the maximum than the other ones, and we see that the behavior before that is within the large statistical errors fairly consistent across the volumes. So definitely, if there's a volume dependency, it is below our large statistical errors, and everything is more or less consistent with each other. We don't have yet any results on different discretizations. That is something we'll need to look out. Don't know what will be happening there. There is some volume dependency at the peak height. We see that the peak goes up the larger the volume is. But again, that may be an artifact of various things. Okay. And now finally, we have determined the result also with different operators. Here, the simplest thing is, of course, to square our fluctuation operators. That is basically what in flat space lattice field theory would be a scattering state of 2 Geons. But we find that the mass is fairly similar between both, except this fluctuation point. There we see a difference, but nonetheless, at times when the universe is fairly large, we see more or less the same result. There's some statistical systematic behavior here, but it's not very large. And that is exactly what we expect if this could be interpreted as a particle-like thing, that we have an independent of the operator. Agreed, this operator is not particularly fancy, so that can be only considered to be a first hint towards that we have particle-like behavior, but at least it's a first interesting hint in this direction. So from that, we assume that this is at least motivating that there could be something like a Geon, and it would be rewarding to have more looks into that. And why should this be rewarding? Because these Geons would have enormous impacts on phenomenology. As I said, one possibility with 0.1 Planck mass, there would be near perfect dark matter candidates, similarly created like primordial black holes. And in particular, our dark matter phenomenology and what we learned from the early universe would quite change if indeed we would have during an inflationary phase that the mass of dark matter should change. So in cosmology, that would be a very, very interesting behavior. But of course, we need more information, especially about the temporal behavior. Of course, such a scenario is bad for indirect detection because it's purely gravitational interacting. And also the question is what happens with this long distance behavior in a especially flat universe like ours. Right now we have a spherical universe. What happens if we go to spatial flat and so on? There's a lot of systematics before we did that. On the other hand, anything which is macroscopic in a pure gravity theory need to be built in the same way. There needs to be an operator which describes any macroscopic object in a quantum theory for which we can calculate it. In particular, black holes have basically two options. Either they have a single operator which creates a black hole, monolithic, and then it has overlap with the operator which we just showed. Or it must be a product of separately different operators. Then you have had Hawking radiation is tunneling. And both of them would be very interesting, but both are the only possibilities which you have. And it's actually the second one is just like building a neutron star operator in QCD, while the first one would be very different. Of course, these are pure gravity black hole like Schwarzschild or Kerr. There's no matter in there. So it's like a Geon star. But as I said, it's very similar, especially the second option, to how you build a neutron star. And that means you have an equation of state for black holes, necessarily. So there may be a signature in terms of gravitational waves. It'd be very interesting to determine that if any of what I said before should turn out to be confirmed. But it also describes how we have to look for that, namely very similar to what we do when you look at neutron stars and look for the QCD equation of state. Okay. Do we have a few more minutes, or is this because 45 is?
No, feel free to go on.
Okay. Okay. Now, it would be amiss if I not put also spin into the perspective which I have here. Because with all of this Brout-Englert-Higgs physics, there is a very interesting connection going on, which we have not yet been looking at CDT, but should be very strongly motivating any effort to talk about fermions in CDT. Usually spin is taken to be a representation of local Lorentz symmetry, except for Kähler fermions, which I will not be considering here. Then you have a second local gauge symmetry, namely Lorentz symmetry. Spin becomes very similar to color. You only have the representations as a distinguishing particle, but the individual components are locally transformable. The usual thing which you would do is coupling by the spin connection. And without torsion, the spin connection is determined by the metric. Now, if we take that, then Brout-Englert-Higgs physics reduces the spin connection again and allows you to have spin emerging as an effective construction. And spin components are then fixed globally, well defined within the non-fluctuating part. And the fact that gravity can locally redefine what spin up and spin down is becomes a very small effect. We know this already from WZ triplets and weak interaction, how this could work. So it is a very interesting possibility why spin components are actually observable in nature, because otherwise this kind of theories would be extremely unclear how this should happen. Now, if you take this for granted, however, the immediate question which you have to ask is why spin at all? Because tangent space in such an invariant formulation is totally unnecessary. So why do we have fermions there? The only thing which has ever been found which necessitates the existence, well, at least in this context, necessitates the existence of fermions is supersymmetry. Now, that becomes a whole other game because the concept of invariant observable carries also to this theory. Physical observables need to be invariant in the local transformations. And this is a surprising application. Combining, if you have gravity with supersymmetry, it makes a local gauge symmetry a local supersymmetry. Two supersymmetry gauge transformations basically make one local diffeomorphism transformation. But supermultiplets are now as Color multiplets. That means the spins of particles can be locally changed by a gauge transformation. So spin being spin 1, being spin 1/2, whatever, cannot be a local observable. It is not gauge invariant, that statement. Composite operators needs to be completely neutral. That means in a supergravity setup, you can never have spin as an observable object. But you could have it as an effectively erasing thing. So consider you have a supergravity multiplet and a scalar multiplet in some linear representation. Any observables need to be invariant under supersymmetry transformation and all others, but this means you have your gravitino and you have, of course, fermions from there. And now supersymmetry is just like color symmetry. It can never be observed directly, but we talk about color because we reconstruct from experiment that it exists, and so we could do this. But individual superpartners can never be detected, just like we cannot detect red versus green quarks, and that could explain why you don't see supersymmetry in experiment. But if you now add the Brout-Englert-Higgs effect and Follisch-Markius-Strocki, then your gravitino field also becomes basically constant. And what you end up with is that a fermion particle from a supermultiplet can still survive and become an effective degree of freedom. Just like what we call the physical Z boson is a condensate-stressed version of the elementary one. And that would allow to explain why you have fermions in nature, why we don't supersymmetry, because you have this combination of these two things. So from that point of view, it becomes very natural to talk about it. So you see that if you take these things seriously, and I think also the existence of this exponential decay in the Geon correlator strongly hints that we have this kind of Brout-Englert-Higgs effect, creates a whole new idea of how flat space quantum field theory can emerge as we are basically, quantum field theory is there because we have the Brout-Englert-Higgs effect. That is, flat space quantum field theory is nothing but the vacuum condensate of quantum gravity in a very loose way. Okay, let me summarize that. The first thing is we need to talk about composite objects because these are the only thing which we can talk about as observables as quantum gravity. Everything else is gauge dependent. And I think the CDT simulations hint that these create reasonable physical degrees of freedom. As I said, it's hint. There's so many systematics we need to discuss before we can make any being sure. But I think it's rewarding because it could be that we really see self-bound gravitons of a mass, so that Geons are real objects. If they exist, if they're temporally spatial, as I said, there is a billion caveats which I have to add here. On the other hand, everything fits very well together with this observed BA effect and FMS mechanism, because that really allows us, first of all, to understand why flat space quantum field theory exists at all. It's not natural. Quantum gravity could really very well have created anything but a theory which creates flat space quantum field theory as a reasonable limit. But just like Newtonian mechanics arises from relativity as a flat space weak field approximation, we see that flat space quantum field theory, standard model of particle physics, could arise as a flat space, as a small quantum fluctuations around a metric in a systematic way, and then the FMS mechanism would allow us to systematically construct deviations from that in a hopefully effective way to access all scales, because CDT will never be able to create the dynamically backcoupling between particle physics and gravity. At least not for the scales which QCD and weak interactions have, fortunately, for computing power types reasons alone. Okay, with that, I'm finished. Thank you for listening.
Yeah, thank you very much, Axel. So feel free to raise your hand if you have questions. I'll turn off the recording in the meantime.